thanks for the organizers for inviting me. Yeah, after 2 talks on non-commutative polynomials, so we'll be back to the commutative world. So I'll be talking about depth 5 circuits. This is a joint work with Christian Engels and Karthik Srinivasaya. Computation model is depth 5 circuits of the form sigma power sigma power sigma, or in other words, any polynomial in this model would look like sum of powers of polynomials, say sum ei, where each of the qj's would look like sum of powers of linear forms. Say 1 to t e to the e of j. Okay. So in the very first talk, we saw a subclass of these polynomials where we have only the depth 3 portion, that is sigma power sigma, and we saw that any sigma power sigma circuit computing the monomial x1 to xn would require size 2 to the n minus 1 to compute the monomial x1 to xn. Okay. Now let me just talk about the importance of this model. So this model, I think the first time we came across was in the Kesam at depth 3 work by Gupta, Kamath, Kayal and Saptarshi, where as an intermediary step in their depth reduction, so their result was arbitrary circuit size S computing a polynomial of degree d can be transformed into a sigma pi sigma circuit over infinite fields of size 2 to the square root of n log of sd times log of n. Yeah. Well, I am missing this constants here, so order of is exponent. Okay. So first step in the argument was applying Agarwal Vinay and improvement by Tavanas. We can transform arbitrary circuit, say a homogeneous circuit. We know that we can assume without loss of generality any circuit computing a small degree polynomial can be assumed to be homogeneous. So this can be transformed into sigma pi sigma circuit where there is a restriction on the fan-in. Of course, this can be done for arbitrary A, B, but of specific interest will be where the fan-in of the product gate is, say, order of root n at both the layers. Okay. Yeah, sorry. Let's say degrees n to simplify. Yeah, right. Yeah, otherwise it will be square root of. Okay. So now applying Fisher's identity that Newton talked about in the very first talk, we can in fact eliminate this product gates with sum of power gates. Or in other words, this can be transformed into a circuit where the only product gates are powering gates, though the depth now becomes 5. Okay. And in fact, it also turns out that the circuit itself is homogeneous. And the blow up in the size is just 2 to the fan in of the product gates. Yeah. So the blow up is 2 to the order. Okay. So in other words, I didn't talk about the blow up here. So the blow up here is known to be 2 to the square root n log of s times log of. Okay. In other words, if it is s is polynomial, then this will be square root n times log n. However, the blow up here is only 2 to the order root n. Yeah, and of course, Gupta et al. Go on further to obtain a depth 3 circuit, though not homogeneous, with only again 2 to the order root n blow up for the same polynomial. Okay. So far in the literature, we have lower bound results for both of these models. Yeah. However, yeah, we don't have, in fact, any non-trivial lower bound results which do not follow from the existing results for the class of depth 5 circuits. Okay. Yeah. So now, of course, with this, it can also be seen that any, say, 2 to the little omega of root n times log n lower bound against such circuits would also imply such a lower bound for depth 4 circuits, which in turn will separate Vp from Vnp. Okay. But however, if you look at the existing lower bound results for depth 5 circuits, depth 4 circuits, they are of the form 2 to the omega root n, and in the case of iterated matrix multiplication, it's 2 n to the omega of root p, where d is the number of matrices in order. Okay. So however, none of these lower bound results translate to a lower bound to this model. At least as far as I could see, there is no translation possible. However, we know that if you prove lower bound against this model, this would imply lower bound against this model. Okay. Now, here comes, one would wonder that it might be possible to extend the lower bound against power sigma circuits, lower bound against x1 to xn for the power sigma circuits to the depth 5 model. Yeah. So here comes a very surprising observation, which was observed by Ram Prasad. In his survey. So in fact, there is a 2 to the order root n size power circuit for x1 to xn. Oh, okay. Okay. So yeah, you had written that this idea is from Michael Forbes, but I was not sure if it is a proof or if there was an observation later on. But anyway. Okay. So in other words, we cannot hope for 2 to the omega of root n lower, let alone 2 to the omega of n lower bound against the depth 5 circuits. We cannot even hope for 2 to the little omega of root n lower bounds against this model. Yeah. However, there is one caveat here. So the depth 4 powering circuit that is obtained is in fact not homogeneous. Okay. Yeah. So I'll just sketch the proof. So the argument is via Newton's identity. So it is known that, so let me have notation first. For d greater than 0, let's denote PD of x1 to xn as the power symmetric polynomial of degree d on n variables. And sim d be the elementary symmetric polynomial of degree d. So Newton's identity allows us to express any elementary symmetric polynomial in terms of power symmetric polynomials. Okay. So in short, the elementary symmetric polynomial of degree d in fact can be written as I as 1 to t, the power symmetric polynomial of degree I times the elementary symmetric polynomial of degree d minus a on the same set of variables. Okay. So if you expand this out recursively, yeah, there is some signs. Yeah, I'll ignore the signs. Yeah, where alpha is a constant. So expanding this out, you can write this as sum of products of power symmetric polynomials, say a1 to ad sum up to such that the overall degree is d. I can write this as some coefficient, let's say c a1 to ad times the powers of the power symmetric polynomial Now the careful observation is the number of summands is at most 2 to the order of root n. Okay? Yeah? So the observation or the crucial observation is number of summands is 2 to the order root n. Yeah. So in other words, any elementary symmetric polynomial has an expression of the form sum of products of power symmetric polynomial. But if you look at it very carefully, this is nothing but a depth 4 circuit where the top fan in is 2 to the number of summands here, number of vectors a1 to ad such that their weighted sum is exactly d, yeah, which turns out to be at most 2 to the order root n. Oh yeah, I missed that part. Yes. This is sigma pi sigma power, but you apply Fisher's identity again. Yeah, sorry, I missed that part. Yes. Yeah, this is sigma product sigma power, but if you apply Fisher's identity again, yeah. In other words, what I was trying to say is like Fisher's identity here in our context is cheap, in the sense that it's only 2 to the order root n, whereas the target lower bounds that we want is 2 to the omega root n. So sorry, yeah, that's true. Yeah, you mean, I mean, you just, yeah, you take x1 to xn and you make it as blocks of root n size, apply Fisher's twice, right? Yeah, that will, you'll get a 2 to the order root n circuit. I'll come to that later. Okay, yeah, that's true. Yeah. Okay, so the only problem here is almost every summand. I mean, so now if I write this as sum of powers again, so almost every summand at the bottom will be sum of powers of sum of the power symmetric polynomials, yeah, and in fact the bottom gate will not be homogeneous, but however the top product gate will be homogeneous. Okay, so if I look at the degree of the top power, or in this case product gate, then it will all be homogeneous. Okay, the only non-homogeneity is at the bottom. So this kind of tells us that even for the depth 4 powering circuits, we cannot hope for better than 2 to the root n size lower bound for the monomial. Or in other words, adding an additional power to the depth 3 circuit, in fact, makes us gain exponentially in the size of the circuit, right? Yeah, in fact, 2 to the n becomes 2 to the root n. So in this work, I don't think so. Yeah, at least as far as I know. Yeah, in this work, we look at the depth 5 circuits, or I mean, what this says is you have to put some restrictions. Yeah. So what we will see is if you put the restriction of homogeneity, then in fact there is a fairly easy lower bound argument. In fact, we will get a 2 to the omega n lower bound. So I will write down our result. So any sigma power sigma circuit. Now I will put restrictions here. I will say that the middle layer of sigma gates has fan in at most n, and there is another kind of weird looking restriction. The bottom powers will have to be at least 21. Okay, I have no answer if you ask me why this number 21. Good point. Yeah, good one. And we'll need the bottom gates to be homogeneous. So any depth 5 circuit with this restriction computing the monomial x1 to xn requires size 2 to the omega n. In fact, it turns out that there seems to be a kind of trade-off between the fan-in of the middle gate and the power gates. So if I increase the minimum degree of the bottom powering gate, we can improve, we can get a lower bound for sigma power sigma circuit, where the fan-in is bounded by 2 to the root n by some constant, yeah, say 2 to the root n by 1000, and the powering is at least root n. We'll get similar lower bound for the same monomial. Yeah, so if you, it looks like if you increase the degree, you can allow larger fan-in. Now, yeah, just a remark on this result. So we'll be in fact proving the first result. The second result is, it follows from a similar argument. However, let me make a remark about the, yeah, interesting fact about this result. So the circuit that Srikanth was pointing out. So in fact, it's not very difficult to see that the monomial x1 to xn, the simplest way to get a powering circuit is, well, I could have applied Fisher's identity right away. I would have got 2 to the n size sigma power sigma circuit. Whereas if I decompose them into blocks, say root n, which turns out to be optimal for this approach. Now I can apply Fisher's identity. I can write each of them as a sigma power sigma circuit of size 2 to the order root n, in fact 2 to the root n. So we'll have a product of sigma power sigma circuits each of size 2 to the root n. Yeah. But the product fan in is at most root n. Yeah. Now if I apply Fisher's again, I'll get a 2 to the order root n circuit of the form sigma power sigma power sigma, where the bottom sigma gates will be homogeneous. And if I look at the middle sigma fan in, this will be 2 to the root n. Okay. Yeah. And in fact, the degree is root n here, degree is root n. The Fisher's identity does not alter the degree. So, in other words, this result says if you reduce the fan in, of course by a factor in the exponent, the lower bound or the size of the circuit has to blow up exponentially, or in other words, the size lower bound is 2 to the omega n, whereas we have a 2 to the order root n size circuit if you have slight increase in the middle fan in. Okay. Yeah, however, I don't really know if this construction is tight, or I don't have any approach of obtaining a lower bound when the middle fan in is say 2 to the root n. Yeah. It could be that our constants could be tightened a bit, but still there seems to be a large constant sitting there. Okay. Yeah. For the rest of the talk, I'll just focus on proving the first result. In fact, the second result follows immediately from the observations or the approach that we take for the first result. So I'll skip that portion. So we'll take the usual measure based approach, which in fact it also turns out that the measure that we define is also natural. So in other words, we cannot hope for we cannot hope for application, I mean this technique applicable for separation of VP and VNP. So define a measure mu f, or measure for polynomials mu, such that mu of any polynomial computed by the depth phi circuits with the restrictions of course is small, whereas mu of x1 to xn is large. Okay. So in addition, if the measure is subadditive, then it's enough to bound the measure for power sigma polynomials. Okay. Yeah. So I'll motivate the measure first. Before defining the measure. So let's look at the power symmetric polynomial of degree d. If we ignore the bottom sigma gates, then any circuit of the form sigma power will be essentially sum of powers of power symmetric polynomials, right? So let's consider a power of the power symmetric polynomial. Okay. Now if I consider, let's say k is some number greater than 0, if I consider a derivative, say t is a subset of cardinality k, so this, in fact, this can be verified that the derivative will look like xi1 etc. xik to the power d minus 1 times ed alpha minus k. Okay. Yeah. Now if you look at the derivative of x1 to xn of the same order, okay, so this is nothing but the product of variables that are not in t, right? So the larger the t, the larger is the support of the monomials in the derivative of the power of power symmetric polynomial, whereas the support of monomials in the product of variables goes down, right? So once you have large support monomials, it's actually easy to handle such polynomials by projecting them down to 0, sum of the variables, right? Or in other words, if I say the support is more than say n half, so if I substitute to half of the variables to 0, all the derivatives of the powers of the power symmetric polynomial will go down. Okay. So that's essentially the motivation for our measure. So we consider derivatives which are projected down to where some of the variables are projected down to 0. Okay. Any questions here? Yeah, so the larger the derivative, we have larger support. So if I take a large set of variables and substitute them to 0, certainly all such monomials will vanish, large support monomials, whereas for the derivative of x1 to xn, those monomials will be intact because the support is smaller. Okay. So formally let's say pi m is a projection of polynomials. This is a multilinear projection. So pi m of f will be in fact summation c alpha x1 to the alpha 1 etc. xn to the alpha n, where alpha 1 to alpha n are 0 1, if f were summation c alpha x1 to the alpha 2 xn to the alpha, or arbitrary alpha. Or in other words, you just look at the polynomial and look at only the multilinear monomials, consider the sum of those monomials with the respective coefficients. Okay. So for any, yeah, so I'll need another projection here. Any subset of the variables, let's denote by pi s the projection of the polynomial where I restrict the polynomial by substituting every variable in S to 0. Okay. Now the measure is defined as EMD KS. K is an arbitrary number. S is a subset of variables, subset of 1 to n. EMDF is the dimension of the span of the derivatives projected down to their multilinear components as well as substitution of the variables in S to 0. Where this is a notation for the set of all derivatives of order k. Yeah. So look at the derivative space and project each of the derivative to each of the derivative to its multilinear components, and then substitute sum of the variables where S is a parameter, a subset of the variables to 0, and look at the span of the polynomials, resulting polynomials. Dimension is the measure. So let's first formalize the intuition we had here. So if I have degree at least 2, then the dimension of the, so this stands for projected multilinear derivative. So projected multilinear derivative of any power of the power symmetric polynomial is in fact, it will be 1 or at most 1 if the cardinality of S plus K is greater than 1. Okay. That follows directly from this observation. So if cardinality of S plus K is greater than n, so any kth order derivative of the power of the power symmetric polynomial will have support, or every monomial there will have support at least k. Now I am substituting variables in S to 0, but since S plus cardinality of S plus k is at least n, so every such monomial with support at least k will be substituted to 0, or in other words every derivative will be killed unless d is 1. In the case d is 1, the derivative is just, PD is just the linear form, so it is just power of the linear form. So yeah, when d is 1, the dimension will be 1, else it will be just 0, or in other words we would have killed all the derivatives. The second observation is the dimension of the multilinear derivatives of x1 to xn. Now I will fix the size of the set. So if I choose k as 3 and 4 and cardinality of S as n by 2, say plus 1, yeah, this can easily be seen that it is at least n by 2 minus 1 choose n. Okay. Yeah, in this case, yes. Yeah. So, I mean, yeah, this is just a toy exercise. I mean, just to understand the measure. Yeah, we are not at to prove this statement. I mean, we are just exploring the measure right now. Yeah, this again is fairly easy to see. Since k is 3 and 4, every derivative will be a product of n over 4 many variables. Okay. So now if I substitute S of the variables in S, which are like n by 2 plus 1 in number, then all the monomials in S complement of degree n by 4 will be surviving as derivatives. So the derivative has so much dimension. Greater than 2, it can't even compute the monomial. So this, I mean, this is kind of not so interesting. So now we'll prove the statement. All we'll do is we'll consider a polynomial of the form power computed by a circuit of the form power sigma. Let's ignore the degree restrictions for the moment. Yeah, we'll parameterize our bounds based on the degree. 1 k 3n over 4, the dimension of the projected multilinear derivatives with respect to k and the subset S to any power of alpha is at most 2 to the some number which is smaller than n by 2. Okay. First, let us see that this would be enough to obtain the first lower bound. So, if we look at the way we have defined measure, it is essentially projection, dimension of projections of derivatives, and we know that the dimension of the derivative space is subadditive. In other words, if I add up two polynomials, the dimension of space of derivatives for the sum is at most sum of the individual derivative spaces. Or in other words, I will just write as another observation, PMD Ks f plus g is at most PMD of f plus, of course with the same parameters. So in other words, combining with observation 2, we know that for the multilinear monomial x1 to xn, the dimension of the derivative space is, this is at least 2 to the n by some constant times root n. Yeah? Oh sorry, n by 2. 2 to the n by 2 minus 1 by some constant times root n. So in other words, it's enough to take any polynomial of this form and bound the derivative, the dimension of the projected multilinear derivative space by a number which is smaller than n by 2 in the exponent. Yeah. So yeah, by so f be any polynomial written as fi, where fi is some projection, say pdi li1 to lin fi to the alpha I, then PMD skf is at most sum of the individual dimensions. This is at most s times this number 2 to the 0.495 n, but PMD sk of x1 to xn is at least 2 to the n by 2 by root up to a constant value. So therefore, s is at least 2 to the n over 2 divided by 2 to the 0.495 whatever. So this is 2 to the n. Yeah. So now all that remains is prove the lemma. Okay. And of course, it's not very difficult to see that this measure is natural. I mean, yeah, this it's kind of easily computable property. How much time I have? 15 more minutes. Okay. power symmetric polynomial. Say f is L1 to the d plus etc. Ln to the d plus some beta. The cardinality of p k. So if I look at the derivative, the multilinear derivative of f with respect to t, this is in fact, if I take the first order derivative, this will look like some coefficient into L1 to the d minus 1 plus etc. some coefficient into Ln to the d minus 1. Okay? Or in other words, any kth order derivative sits in the span of the powers of linear forms Li to the d minus k. Right? Yeah? So I'll keep this as point 1. Yeah. So now I'll write another lemma which in fact gives a basis for the projected multilinear derivative space of the powers of power symmetric polynomial. Let's say f is L1 to the d plus etc. plus Ln to the d plus beta. LJB homogeneous linear forms. Let's say y is set of all powers of this form Li to d minus j, where j is at most min of d and k, and let's have a value epsilon which is at most 1/4, a non-zero value. And the value of k will fix as 3 and 4. Cardinality of S is n by 2 plus 1. Then the projections of multilinear derivatives of order k del ml of f to the alpha is contained in the set the projections multilinear and substitution to 0 of the set of polynomials of the form. So I have powers of f, let's say alpha minus I, where I is a value between 1 and k, and abusing the notation again, this is not tensor product, this is a pairwise product of polynomials in the set. Indexed by S complement, and m less than or equal to some number is monomials of degree most. Okay, so let me read this out loud. So this lemma states or gives us a nice or possibly simple basis for the derivatives or projections of derivative space of f to the alpha. In other words, we can just ignore the projection part here. It's just, so derivative space is spanned by products of polynomials of the form f to the alpha minus I with, so this is set of all monomials in the variables which are not in S of degree at most lambda n, union with set of all monomials but in variables from the set y. Remember that y is just powers of the linear forms. Yeah. So size of y is n times d at most. Or in other words, any projection of derivative can be written as a linear combination of product of a polynomial here and monomials from here. Okay. So let me just assume this and conclude the proof of lemma. So by lemma 2, the dimension of projected multilinear derivatives of f to the alpha is at most size of the first set, which is at most k times size of the set of all multilinear monomials in S bar of degree at least lambda n plus number of monomials of degree at most 1 plus epsilon times n by d in the variable y. Okay. So this is at most k times. So number of monomials in S complement is, number of variables in S complement is n by 2 minus 1. So this will be at most n by 2 minus 1, choose lambda n up to a linear factor. So it's at most n times n by 2 choose lambda n plus this will be at most the number of variables is dn plus 1 plus epsilon times n by d, choose 1 plus epsilon times n by d. Okay. So I didn't say what is lambda here. Lambda here is 1 over 4 plus epsilon, okay, where epsilon is a value strictly less than 1/4. So this value is exponentially smaller than 2 to the n over 2, right? Because lambda n is slightly, or an epsilon n fact additive term away from n by 2. So this will be roughly, depending on what we choose as epsilon. Say if you choose epsilon as 0.1, this will be something like 0.495 n in the exponent. Now this is where the d greater than or equal to 21 comes into the picture. Okay. So this value is 2 to the n by 2 minus omega n if d is at least 21. Okay. So in fact Ramprasad and Surajit have improved the bound slightly. I mean, this looks like a brute force bound. So if you calculate the parameters better, then as far as I know, you can improve this to d greater than or equal to 19. But like I said, apart from the fact that 21 is 42 by 2 or 7 into 3, I have no idea why it is 21. Okay. So I guess I have 7 to 8 minutes. time on proving this. Take an arbitrary subset P of variables of cardinality K. So let us stare at the derivative of f to the alpha with respect to the variable C. Yeah, I'll not write the exact expression. Let's take the example when t is 2. Say t is 1 and 2. That's variables x1 and x2. So the first order derivative of f to the alpha with respect to x1 would be alpha times f to the alpha minus 1 times the derivative of it, right, which looks like modulo the coefficients or modulo the constant terms, L1 to the d minus 1 plus etc. Ln to the d minus 1. Okay. Now if I derive this again, say with respect to x2, yeah, like I said, I'm just ignoring the constant terms. This will be derivative of this polynomial with respect to x2. Okay. So now I'll have to apply the product rule, right? Either I derive f to the alpha minus 1 again or the powers of linear forms. Okay. So this will be in fact in the span. Like I said, it's painful to write down the coefficients. Span of f to the alpha minus 2 times L1 to the d minus 1 plus etc. Ln to the d minus 1, or f to the alpha minus 1 times L1 to the d minus 2 etc. Ln to the d minus 2. Right? Make sense? Okay. So in other words, for an arbitrary t of size k, the derivative of f to the alpha with respect to t is in the span of, yeah, any guesses? You'll have all powers of f, alpha minus 1, alpha minus 2, etc., alpha minus at most k, right? If I derive it to the order k, I'll have the least power that I'll have of f will be f to the alpha minus k. And what are the least power of linear forms I'll have? D minus k, right? If k is greater than d, then yeah, it will be at most 1, or sorry, at least 1. Okay. So this will be in the span of, use this space, the union I equal to 1 to k f to the alpha minus k. Okay. This multiplied with, again abusing the notation, I'll just denote it with the symbol for tensor product. Okay. With the product of linear form, powers of linear forms of the form L1 to the d minus 1, L1 to the d minus 2, etc., 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 right? Whereas, so it will look like product of let's say j equal to 1 to k L I j to the d minus could be j, yeah, where, well, this is not quite correct. Yeah, I'll write it in more precise form. So this is the product of polynomials of the form f t of let's say tj, where t1 union etc. or ti etc. tj is t, okay, where ft is the derivative of f with respect to t. That's the simplest way to write it. Okay? Or in other words, for the derivation by product rule, I'll be deriving copies of f so many times. So cardinality of t1 times, cardinality of t2 times, etc., etc. Okay? Yeah, it's just a notation. I hope it is fine. Yeah, otherwise it's a bit painful to write it explicitly in terms of powers of linear forms. Focus on this portion, this product of derivatives. So let's say I have a partition of the variables t1 etc. say ti, where each of the set is non-empty or part is non-empty. Then if I look at the product j equal to 1 to I, the derivative of f with respect to ti, okay, I can write it as r times f, let's say, yeah, I'll again need a notation here. Okay, so what I do is I collect the sets of cardinality, given cardinality R. Okay, so I'll have a notation f to the R, okay, where not R, tr, where tr is the number of sets with cardinality R. So I'm just rewriting this expression now. So if I look at the cardinality of ti is at most 1 to k, right? So I'll split this product with respect to the cardinality of the sets in the variable ti. So I can just write it this way. So this could be for some representative. Yeah, what I mean to say is, for the, say, for a rth order derivative of f, yeah, so it really does not matter with respect to which variable I derive. Okay, so if I look at this expression, it really does not matter with respect to which variable I derive. All I care about is a linear combination, I mean a basis for the set, or in other words, I don't really care about, so if I derive, say, L1 to the d with respect to any variable, yeah, it will be it will be in the span of L1 to the, say, the order is k, then L1 to the d minus k, right? So in other words, here it really does not matter with respect to which variable I derive, right? So any arbitrary representative set of cardinality R would be enough. Yeah? Well, I should not write it this way. It's in the span of. It's incorrect to write it that way. Yeah? So if I'm bothered only about the linear combinations, then it's all this. Okay? Yeah. So f to the alpha as a linear combination of the polynomials of the form union of polynomials f to the whatever f to the alpha minus I. Okay. Then I can just write. So if I look at this polynomial, the derivative of f of order r is nothing but in the it is in the span of L1 to the d minus r etc. Ln to the d minus r. So I could just write this as a product of the form, let's say r is 1 to at most k Lr multiplied with itself r many times, where Lr is simply the set L1 to the alpha minus r etc. Ln to the alpha minus r. Yeah. Again, I forgot to write the span, so it won't make sense. The constants won't match. Yeah. So now all we will do is we'll just ignore this portion. We'll just stare at products of this form. Okay. So you can just imagine these as variables. So what I am looking at is monomials on these. So I just visualize them as formal variables. Monomials in these formal variables. So the number of formal variables is exactly n times d. Okay. Yeah. So now we'll. I'll just take 2 minutes to just. Yeah. Okay, so now what we'll do is we'll just look at the projections of the products of the form 1 to k Lr tensor some number. Okay. Yeah. So here the only thing is, when we look at the derivatives, the sum of, I mean, you can just imagine Jr is the number of times I'll take rth order derivative of f. Yeah. So the orders should match, or in other words, summation r Jr r equal to 1 to k should be the total order. Okay. That's the only thing really matters here. So this will be in fact equal to k. Okay. So the only crucial part is to obtain a basis here. I could have just taken this as formal variables and obtained all monomials of whatever degree k. Okay, but that will be a really bad basis. Okay, so now what you do is, this order really matters, of course. Yeah, what we really do is, under the projection we can eliminate all the monomials of large degree. Okay, so now if degree of this product is greater than n by 2, then I know that the projection kills it right away, right? Because the support of the monomials will also be at least n by 2. Now if the degree is j equal to 1 to k Lr to the Jr, if the degree is say at least lambda n, at most n by 2, then I can span it by then the corresponding polynomial is in the span of monomials of degree at most, multilinear monomials of degree at least lambda n in the remaining set of variables which are not present in S. Okay? Yeah. Now, if none of these conditions met, I know that the degree of this term is at most lambda. Okay. Yeah. Now, the crucial point is LR itself consists of linear forms of the form degree alpha minus d minus r. Okay. Yeah. So now if I look at the overall degree is lambda n. So if I look at any monomial here, the degree of the monomial will be in not monomial, let's say term. The product j equal to 1 to k LR tensor JR will be in fact summation d minus r times JR, which I know that is at most lambda. Okay. Yeah. So this implies d times summation JR is at most lambda n plus summation r JR, which is at most k. In fact, it is equal to k. So this is lambda n plus k, which is 3/4 of n. This is 1 plus epsilon times n. Okay. Or in other words, now if I just imagine these LIs as formal variables, yeah, I can have monomials of degree at most this divided by d. No, sorry. This implies summation JR is at most 1 plus epsilon times n over d. Okay. Or in other words, I just need to consider products of this Li to the d minus r of support at most this number 1 plus epsilon times n by d. Okay. Yeah. So that was the portion here. Okay. So the other portion is of degree at least lambda n. This portion is the powers of f. Okay. Yeah, that's all. Yeah. I'm sorry for the. Yeah, I thought I would do a better job doing board. I think I should have done 2 slides. Yeah. The symbols were too much. Okay. Why we worked up was because of the derivatives of powers of power symmetric polynomial. It just gets larger support. That is how we came to this. We didn't really study this model systematically. We were looking at projections of power symmetric polynomials and powers of them. So yeah, I don't really have any intuition about why smaller depth would be useful, or at least. But to think about, I really like about this power model. Rather than the